Imagine a machine that learns like we do, recognizing faces, understanding language, even driving cars. At the heart of this dream are neural networks inspired by the human brain's billions of interconnected neurons. These artificial networks learn from data, identifying patterns and improving over time. This ability to learn makes them powerful tools, but their journey has been full of challenges. Today we'll explore how neural networks evolved from simple models to the driving force behind modern AI. Join us as we uncover the fascinating history of neural networks. Our story begins in the mid-20th century when computers were just emerging and scientists wondered if machines could think like humans. Inspired by the brain's network of neurons, researchers set out to create artificial neural networks, despite primitive computers and scarce data. This is the story of their vision, setbacks, and breakthroughs that shaped the future of AI. In 1943, Warren McCulloch and Walter Pitts introduced a mathematical model of the neuron, a simple on-off switch that fired if inputs were strong enough. Their model showed that networks of these artificial neurons could perform logical operations, hinting at the brain's computational power. Though limited by the technology of their time, their work planted the seed for artificial intelligence. The idea, simple units, connected together, could solve complex problems. The dream of machines mimicking the brain was now a real possibility. In 1949, Donald Hebb proposed that neurons learn by strengthening connections when they fire together, a concept now known as Hebbian learning. This idea explained how networks could learn from experience, not just mimic structure. Hebb's insight paved the way for learning algorithms that would power future neural networks. The field of AI was gaining momentum, fueled by each new discovery. In 1956, visionaries gathered at Dartmouth College for a workshop that marked the birth of artificial intelligence as a field. The term artificial intelligence was coined, and neural networks were a central topic. These pioneers debated, collaborated, and set the stage for decades of research. The Dartmouth workshop ignited a passion for AI and fostered a spirit of innovation. It was a turning point that launched an era of rapid progress. In 1957, Frank Rosenblatt unveiled the Perceptron, the first working artificial neural network capable of learning. Designed to recognize patterns, the Perceptron learned from labeled examples like distinguishing apples from oranges. It made headlines and sparked public imagination, suggesting true AI was within reach. The Perceptron brought neural networks from theory to reality, fueling optimism and investment. The future of intelligent machines seemed limitless. The Perceptron was a network of simple nodes, each weighing inputs and producing outputs based on thresholds. Its learning ability came from adjusting these weights with each new example, a process called supervised learning. Though basic, it could solve simple classification problems and demonstrated that machines could learn. The Perceptron's design inspired a wave of research into more capable neural networks. It was a foundational step toward intelligent machines. The Perceptron's simplicity made it accessible and easy to build upon, inspiring researchers worldwide. It hinted at a future where machines could recognize handwriting, translate languages, or diagnose diseases. The Perceptron became a symbol of AI's promise, igniting excitement and optimism. It showed that brain-inspired principles could be turned into working technology. But the Perceptron hit a wall. The XOR problem, a simple task it couldn't solve due to its linear structure. Critics seized on this limitation, arguing the perceptron was far from true intelligence. The excitement faded as the field faced unforeseen challenges. The dream of intelligent machines seemed more distant than ever. Despite setbacks, researchers saw the perceptron as a crucial first step. Its limitations spurred the search for more complex, multi-layered networks capable of learning non-linear patterns. This period laid the groundwork for deep learning, even as doubt crept in. The quest for smarter machines continued, driven by human ingenuity. Early networks like the perceptron struggled with real-world tasks, recognizing objects, understanding language, due to limited computing power, data, and algorithms. Training was like teaching a child with only a few blurry photos and simple words. As limitations became clear, optimism gave way to a sobering reality. The field faced growing disillusionment. Our critics, including Marvin Minsky, argued neural networks had overpromised and underdelivered. Their 1969 book Perceptrons highlighted fundamental flaws, like the XOR problem, casting doubt on the field. Funding dried up as attention shifted to other AI approaches. The dream of intelligent machines seemed to be slipping away. Technical challenges and criticism led to the AI winter, a period of stagnation and dwindling support for neural networks. Research slowed, labs closed, and many left the field, yet a small group of dedicated researchers persisted, believing in the potential of neural networks. Even in the darkest times, the seeds of innovation remained. Their perseverance would one day reignite the AI revolution. The AI winter, while a period of stagnation, also provided an opportunity for reflection and reassessment. Researchers began to analyze the reasons behind the limitations of early networks and explore new ideas and approaches. They recognized the need for more robust learning algorithms, more powerful computers, and larger, more diverse datasets. One important development during this time was the emergence of Connectionism, a school of thought that emphasized the importance of distributed representations and parallel processing in artificial intelligence. Connectionists argued that intelligence arises not from the manipulation of symbols, as was the prevailing view at the time, but from the complex interactions of many simple processing units similar to neurons in the brain. This shift in perspective paved the way for the development of new neural network architectures and learning algorithms that would eventually lead to the resurgence of the field. Researchers began to explore networks with multiple layers, more complex connections, and novel learning rules inspired by biological systems. The AI winter, though a trying time, proved to be a period of crucial development. It forced researchers to confront the limitations of their approaches, leading to a deeper understanding of the challenges of artificial intelligence and the development of new ideas that would eventually pave the way for the deep learning revolution. The seeds of innovation sown during a time of adversity were about to bear fruit. As the AI winter cast a long shadow over the field, a pivotal breakthrough was about to emerge. One that would breathe new life into neural networks. In the early 1980s, a powerful learning algorithm called backpropagation was rediscovered and refined, igniting a renewed sense of hope for the future of artificial intelligence. The origins of backpropagation can be traced back to the 1960s and 70s. But it was in 1986 that researchers David Rumelhart, Jeffrey Hinton, and Ronald Williams, along with their colleagues, published a seminal paper that brought backpropagation to the forefront of neural network research. Their paper demonstrated the power of backpropagation in training multi-layered networks, overcoming the limitations that had plagued earlier models, like the Perceptron. Imagine a network of interconnected nodes arranged in layers, with each connection between nodes having a certain strength or weight. These weights determine how signals flow through the network, influencing its output. Backpropagation provided a way to systematically adjust these weights layer by layer based on the network's performance on a given task. This breakthrough was revolutionary. Backpropagation provided a way to train complex multi-layered neural networks, enabling them to learn intricate patterns and solve problems that were previously considered intractable for artificial intelligence. The rediscovery of backpropagation marked a turning point, a beacon of light amidst the darkness of the AI winter. To understand the significance of backpropagation, imagine teaching a child to ride a bike. You wouldn't simply place them on the bike and expect them to ride off effortlessly. You would guide them, correcting their balance, adjusting their grip on the handlebars, and providing encouragement along the way. Backpropagation acts as a similar guiding force in training neural networks. The process begins by feeding the network with labeled data, like images of cats and dogs with their corresponding labels. As the network processes the data, it makes predictions, initially with a high degree of error. Backpropagation then calculates the difference between the network's predictions and the actual labels, a measure of its error. Here's where the magic happens. Backpropagation propagates this error signal back through the layers of the network, adjusting the weights of the connections between nodes to minimize the overall error. It's like fine-tuning the gears of a complex machine, making subtle adjustments to improve its performance. This iterative process of feeding data forward, calculating error, and propagating it backward continues until the network's predictions become increasingly accurate. The beauty of backpropagation lies in its ability to automatically adjust the network's parameters, learning from its mistakes and improving its performance over time. Backpropagation, with its ability to train multi-layered networks, unlocked the true potential of neural networks, enabling them to tackle problems that had long stymied the field of artificial intelligence. Researchers could now build networks with hidden layers of nodes that weren't directly connected to the input or output, allowing them to learn hierarchical representations of data. Imagine a network learning to recognize faces. The initial layers might learn to detect simple features like edges and corners, while deeper layers combine these features to recognize more complex patterns like eyes, noses, and mouths. Finally, the output layer uses this hierarchical representation to identify the specific face. This ability to learn hierarchical representations was a game changer. It allowed neural networks to extract meaningful features from raw data, making them more powerful and versatile than ever before. They could now tackle a wider range of tasks, from image recognition and speech synthesis to natural language processing and machine translation. The impact of backpropagation was profound. It breathed new life into the field of neural networks, transforming them from theoretical curiosities into powerful tools with practical applications. The AI winter was beginning to thaw, and a new era of research and innovation was dawning. Despite the breakthrough of backpropagation, the resurgence of neural networks was not immediate. The AI winter had taken its toll, leaving the field with limited funding and a lingering sense of skepticism. Researchers faced an uphill battle, struggling to convince their peers and funding agencies of the potential of this revitalized approach to artificial intelligence. The computers of the time were still relatively slow, making it computationally expensive to train large, complex networks. Data, the lifeblood of machine learning, was also scarce, limiting the ability to train networks on the massive datasets required for them to reach their full potential. Nevertheless, a dedicated group of researchers persisted, driven by a belief in the power of neural networks to revolutionize artificial intelligence. They continued to refine backpropagation, develop new architectures, and explore new applications, laying the groundwork for the deep learning revolution that was to come. The seeds of a revolution had been sown. Backpropagation had provided the key to unlocking the potential of neural networks, and while the world was slow to notice, the field was quietly gaining momentum. A new era was dawning, an era where machines would learn to see, hear, understand, and even think, transforming the world as we knew it. While the world remained largely unaware, a quiet revolution was brewing in artificial intelligence. Neural networks, once on the fringes, began to prove their worth. Armed with backpropagation, researchers found success in handwriting and speech recognition. In the early 1990s, Jan LeCun's LeNet 5 could recognize handwritten digits, revolutionizing check processing. Speech recognition also advanced, paving the way for future voice assistants. These breakthroughs laid the foundation for the deep learning revolution to come. Imagine building a skyscraper with only hand tools. That's what early neural network researchers faced, limited by the computers of their time. But as computers evolved, processing power exploded, fueling a new era for neural networks. Moore's law drove exponential growth, making once impossible computations possible. GPUs, built for gaming, became perfect for neural networks, unlocking deep learning's true potential. Imagine teaching a child to speak with just a handful of words. That's what early neural networks faced: limited data. But the digital age brought big data, an explosion of information from the internet, social media, and digital devices. Every click and interaction became fuel for learning algorithms. Combined with powerful computers, neural networks could finally learn complex patterns. This feast of data and computing power sparked the deep learning revolution, transforming artificial intelligence. The early successes, combined with the advancements in computing power and the availability of big data, led to a fundamental shift in the field of neural networks. Researchers began to explore deeper and more complex architectures, moving away from the shallow networks of the past. This marked the transition from the era of neural networks to the era of deep learning. Deep learning, as the name suggests, involves training neural networks with many layers, often tens or even hundreds of layers deep. Each layer learns to extract increasingly abstract and complex features from the data, creating a hierarchical representation that captures the underlying patterns and relationships. This shift towards deep learning was driven by the realization that deeper networks, with their ability to learn hierarchical representations, could achieve significantly better performance on a wide range of tasks. Image recognition models could now identify objects with human-level accuracy, while natural language processing models could generate human-quality text and translate languages with remarkable fluency. The stage was set for a revolution. Deep learning, fueled by big data, empowered by advancements in computing power, and driven by a dedicated community of researchers, was about to transform the world as we knew it. The quiet revolution was about to become very loud indeed. The era of deep learning had begun. From the spark of an idea, mimicking the human brain, to the rise of artificial intelligence, this is a story of perseverance and ingenuity. Pioneers dared to dream of machines that could learn, facing setbacks and skepticism, but never losing faith. From the Perceptron to deep learning, each step built on the last. Even through the AI winter, progress continued, leading to new breakthroughs. Today, we witness the ascent of AI, powered by the vision and persistence of those who came before. Neural networks are now part of our everyday lives, powering search engines, translating languages, recommending movies, and even driving our cars. But this is just the beginning. Deep learning is still young, full of untapped potential and unexplored frontiers. As we explore the mysteries of the brain, we find new ways to mimic its abilities. Machines can now see, hear, understand, and even think. The future of AI holds immense possibilities and responsibilities. The journey ahead is filled with wonder and possibility.